Hello, everybody, and welcome back to Math 100. Today, we are going to start Chapter 4, and we will, of course, start with the first section, in Section 4.1, where we study basics of probability. So Chapter 4 is all about probability, randomness, expected values, and risk. All right, we don't know the future, but we can certainly understand tendencies. Okay, so probability, another important concept in practical life. So let's get started with section 4.1. All right, chapter 4 is about probability, and in section 1, we will study the basics of probability, right? Okay, so the main question, what is the main question that we are going to ask today? How do you calculate chances, risks and odds? Can mathematics describe randomness? And those are the things that we will be asking. And I would say in the last 300 years or so, starting with people like Pascal and mathematicians who are interested in lotteries and gambling and so on, for the last 300 years or so, the probability theory as a branch of mathematics has been developed quite extensively. And so here's what we know today. We can't predict the future. Of course, you knew that, right? But we can measure and quantify randomness. In a sense, we can tame and understand randomness so that when things happen in a strange way, in a way that doesn't seem to be random, we can quantify it, and we can quantify and say things like, you know what, something is wrong, something is rigged, and so on. Okay, so the basics. All right, let's start with some basic ideas. Suppose E is an event. See, when we talk about probabilities, we talk about the probability or the chances that something would happen, right? That something is called an event. So capital E represents an event, and that could be anything that might happen. All right. So if E is impossible, we say the probability of E is equal to, what do you think? Of course, 0, right? The probability 0 means it will never happen. And if something is certain to happen, then the probability of that event is 1. That is 100%. Okay, when we are 100% certain something is going to happen, then of course we say the probability is 1. All right, and then all the other probabilities will be between 0 and 1, right? So this is an inequality that we can write. Is that right? Well, not quite, right? Because sometimes the probability can be equal to 0. Some things will never happen. Can today be both Sunday and Wednesday? The answer, no. The probability of that happening is 0, right? And then the probability of certain things is 1. And so that would be equal to 1. Okay, so an outcome. Now there's a difference between the word outcome and an event in the theory of probability. All right. So when we talk about an outcome, we are talking about the most basic, like an atomic level, unsplittable, okay, most basic possible result. And an event is one or more of those outcomes. Okay, let me give you an example so you can understand the difference between these two important terms. Okay, an outcome and an event. Right. Let's say you flip a coin 3 times. Okay, so you have this coin, you flip it 3 times, and of course, in each of the flips, you can get heads or tails, right? But when you have this trial or an experiment called flipping a coin 3 times, there are, it turns out, 8 outcomes. Now, why 8? Okay, I will explain that in just a second. But I want you to know for each one, you have 2 outcomes. But because you're doing this 3, okay, you will have 8 outcomes. Let's go ahead and list all 8 of them. Now, it's quite possible that you can get heads, 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 right? And then you can have heads, heads, tails. And by the way, these are the only two cases when you have two heads in a row to start the flips with, right? So you can have heads, tails, heads, heads, tails, tails. Okay, now I have listed 4 in which you have heads in the first flip. Okay, so the other 4 would have tails at the beginning. Tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay. Did you get the idea? And if you look at this, you see that I am writing this in the alphabetical order. This is called the sometimes the lexicographical order. And it's sort of nice to keep that in mind, or to have some structure as you list all the outcomes, because many times you may have a duplicate or a missing outcome if you just choose them at random. All right, I'm going to give you another way to understand this, and this is called a tree diagram. Some of you may remember this from your math class in high school or something. At the beginning, you can have heads or tails, right? Now, if you get the heads first, for the second one, you can also get heads or tails. If you get the tails first, you can still get heads or tails independently of your first flip. And then if you have HH, you can have H or T for your third flip, and HT, HT. For each of these 4 outcomes for the first 2 flips, you can have 2 different choices here. And if you notice here, this is called a tree diagram for an obvious reason. In each step, things are branching off. In each step, you have 2 branches growing from one, one letter of the alphabet. And so you have 1, 2, 3, 4, 5, 6, 7, 8. And those are the 8 outcomes. Now you can tell this is going to grow very quickly. It's a fast growing tree because if you have, for instance, you flip the coin 10 times, you have 2 to the 10 outcomes. The reason this is 8 is because it's 2 to the 3rd. Okay, in other words, you're flipping the coin 3 times. This could be heads or tails. This could be heads or tails. This could be heads or tails. So it's 2 times 2 times 2. In the later section, we will learn how to count these numbers, right? And so we will wait until then to address more difficult problems of counting. All right. So now in continuing with this flipping the coin 3 times, let's see, what is the probability of all tails? Can you see that? Out of these 8 outcomes, by the way, these, if the coin is a fair coin, then these will happen with equal probability, all 8 of them. Okay, so the probability that one of them could happen is 1/8, all right? So all tails, that's only the last one, right? So all the probability that you get 3 tails in a row, all tails, is 1/8. Not bad, right? It makes sense. What is the probability that it ends with the heads? Right? So you can count. If you have listed all the possibilities, you have 1, 2, 3, and 4. Right? So that's 4 out of 8, right? And of course, that is equal to 1/2. And that's not surprising either, because after all, it doesn't matter what you get in the first 2 flips, right? On the very last one, what is the probability it ends with the heads? Well, you can have heads or tails for the last one independent of the first 2, and therefore the probability that the last one turns out to be heads is 1/2. All right, extra. What is the probability of 4 heads if 4 coins are tossed? Think about this. So far we have had 3 coins, right? So 2, I said 2 to the 3rd is 8. Not very pretty here. Okay, but if you have 4 coins, or if you flip the coin 4 times, there will be altogether 2 times 2 times 2 times 2. Altogether, there will be 16 outcomes. And out of the 16 outcomes, how many outcomes fit this description? 4 heads. Well, basically, the only way you can get 4 heads is heads, 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 heads. That's 1 out of 16, and therefore the probability is 1 out of 16. That's pretty simple, I think, right? All right, so here's a general formula, which is not even really a formula. I mean, this is just, how should I say this? This is just a common sense rule, if you will, right? And so this is a long, what am I doing here? I am trying to define the long fraction, okay? And so on the top, I will write number of outcomes representing E. Don't copy yet. Okay, this is it. Right, so on the top is a number of outcomes representing E. And in the denominator, you have the total number of outcomes. All right, I hope this makes sense. That's what we did in all of these cases above. So for instance, what is the probability of getting all tails in 3 coin flips? Well, that's 1 because HHH is the only outcome representing that event. And then the denominator was the total number of outcomes, which is 8. Okay, so now I guess I should mention, going back to the difference between outcome and event. Each of these 8 results is called an outcome. Okay, now also each of them is an event by itself. Okay, but an event could be 1 or more outcomes. So for instance, we talked about ending with the heads, right? So that's this, 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 and this. So 4 of the 8 outcomes in this case represents that event. And that's what the difference is between an event and an outcome, right? Again, that's not a very difficult thing to comprehend, I don't think. All right, so what kind of probabilities do we have? We focus in this chapter on theoretical or mathematical probabilities, the probabilities that we can compute. Okay, but in real life, probabilities could depend on what we observe, what we collect in as data. Now we talk a lot about data in chapter 5, statistics, but once you have a set of data, you can use that or those numbers or figures as a empirical probabilities, right? So this is the idea called empirical. Empirical means based on observation, okay? Empirical probabilities. So take a look at this chart, which represent real, true numbers, okay? So this represents 3 former NBA players and their free throw percentages, actual figures, all right? And so, and of course, one is not as good as the other 2. You could probably guess which one if you are a basketball fan. Michael Jordan. So he has, well, he attempted 8,772 free throws, of which he made 7,327. Okay, so if you divide 7,327 by 8,772, you get 0.835, which is in sports news, they will of course use percentages, and they will say the probability is 83.5%, or we will just call it 0.835. Right? Kobe Bryant, another phenom, and unfortunately he has passed away, as you know. 8,378 successful free throws out of the 10,011. And so if you divide these numbers, you get 0.837, okay? And you can see like 83% is a pretty good number for these professional players. Shaquille O'Neal is another story. He, if you divide 5,935 successful throws made by the number of attempts, you get 0.527. I am not denying he was a great player, but as far as the free throw percentages are concerned, he is not at par with the other 2. Okay, but anyway, this kind of idea is called empirical probabilities. Now, this is important, you know, when you do like weather forecast or probabilities of a hitter going reaching base in baseball and things like that. Okay, another important concept, this is actually quite useful in calculations of probabilities, is called a complementary event. And this, if you remember from chapter 1, that this thing here, that's the negation, right? So E is an event, and the negation of E is the negation of the event. That's the opposite of the event E, and that means we are talking about the probability that E does not happen. All right. Now, it probably comes to you very natural if to understand that the probability of E not happening is, or the probability of the negation of E is 1 minus the probability of E, right? In other words, if E has a 90% chance of occurring, then the probability that E does not happen is 10%. Very clear, right? So it is the negation. It's the same concept. Find the probability that you do not get a 1 in the roll of a die. Okay, now when you roll a die, and I'm thinking of the basic, standard 6-sided die. The plural is dice, right? So you have like 1, 2, 3, and 4, 5, 6, and so on. What is the probability of getting a 1? Well, it's 1/6, right? So what's the probability of not getting a 1? That should be 1 minus 1/6, which is 5/6. And again, that should be pretty intuitive, okay? Find the probability that you get at least 1 tails when you toss 3 coins. Now, this may be a little harder problem for you. One way to look at that, to consider this, is to look at all the 8 possibilities here, and then think of, how many of these outcomes represent this event that you get at least 1 tail. But think about this, okay? Let me go ahead and write this down in English using words, right? At least 1 tail is the negation of what? What is the way, or what are the all possible ways of not getting at least 1 tails? At least 1 tails means 1 tail is okay, 2 is okay, 3 is okay, right? So the only way to not get at least 1 tails is if it's all heads. Get that? The opposite of at least 1 is all heads. Ah, that sounds familiar, huh? Yeah, it should sound familiar because we learned this in chapter 1. In chapter 1, we learned that the opposite of having at least 1 tails, or there are some tails, is, the negation is what? No tails, okay? That means all heads. And so the negation is all heads. And what is the probability of having all heads? We calculated that already. Let's see, with the probability 1/8, right? The probability of getting all heads was 1/8. And so the probability of at least 1 tail is equal to 1 minus 1/8, which is 7/8. Okay, so that is how you get the answer. And the complementary probabilities turn out to be a very useful, convenient tools in calculating certain probabilities. All right, so let's go to the next page. I want you to look at this part, this first bullet point. A standard deck of cards, and I assume that many of you, if not all of you, are familiar with a standard deck of cards, but because we serve many different groups of students from many different diverse backgrounds, it's sometimes possible, it's understandable, some of you may not be familiar with a standard deck of cards. So just as a background, a standard deck of cards contains 4 suits. You have hearts, diamonds, spades, and clubs, and each of them has 13 values. All right, so we have ace, which represents 1, and sometimes it is the highest number, sometimes it's the lowest value. And then you have 2, 3, 4, 5, 6, 7, 8, 9, and 10, the numerical cards. And then you have a jack, a queen, and a king. Sometimes this is called 11, 12, and 13. All right, so 4 times 13, we have, of course, 52 cards plus the joker or jokers, but we will not consider those as a part of the standard deck of cards. And I want you to answer, these two questions. What's the probability that a randomly drawn card is a king? And how about its spade? How about the queen of clubs? It's very specific. Or how about 7, 8, or 9 of any suits? Okay, so try to, I mean, these are sort of easy questions, and go ahead and try these, and then start up your next section or part 2 of this video.